Okay, this is David Zierler, Director of the Caltech Heritage Project. It's Tuesday, June 7th, 2022. It's great to be back with Dr. Thomas Miller. Tom, great to be with you again. Thank you for joining me.
Thank you, David. Good to be back.
Tom, we're going to pick up from at the point at Oxford when you defended your thesis. When it was time for you to start thinking about next opportunities, did you think about staying in the UK? Was that an attractive option at that point?
Um, I did not. Well, but by that point, I just got married right at the very end of my time in the UK in 2005. My wife is English, but it was always we basically planned to come back to the US, and we considered whether or not to go to one position in New York or another position in the Bay Area, and we eventually went to the Bay Area. But yeah, I think it was. Well, we love the time in the UK. It's strong times, but because she'd grown up in Belgium, the UK didn't have as strong a lure, I guess.
What was it about Berkeley? Was it a professor you wanted to work with, the research culture? What was the draw there?
Yeah, in my field of theoretical chemistry, there were two absolutely eminent scientists, Bill Miller and David Chandler. They had agreed to take me on as a joint postdoc between the two of them, and it was a very special opportunity.
What was your research at that point? What did you want to do when you got to Berkeley?
Yeah, I think I basically wanted to continue on the journey of taking the methods and general strategies that I'd been doing during my PhD and taking them into ever more complex systems. So, David Chandler specialized in statistical mechanics, the description of complexity in molecular systems. Bill Miller was just an absolute, leader in terms of the more fundamental aspects of chemical dynamics. They really were two halves of the coin of theoretical chemistry in a way that was a lot of fun. Berkeley's a special place too. Yeah.
Being in the Bay Area, just to foreshadow to 2020, was startup culture, was entrepreneurialism, was that in the air? Was that sort of part of your world at all?
I'm sure it was in the air. It was not a part of my world. I remember distinctly, being in Oxford, and I remember David Chandler visiting one time and saying that, you know, Oxford should do more in terms of entrepreneurialism, which is kind of funny because he never did anything in terms of entrepreneurialism at Berkeley, even though I guess he was surrounded by more of the Bay Area vibe. It was there, but I didn't pick it up, I would say. Very one track mind.
What was the main research that you did during your postdoc? What were you focused on at that point?
Yeah, I had this vision that I'd somehow, take those two great professors and we'd all work together on a grand problem. And the reality is I just worked on two different problems. With Bill Miller, I worked on dynamics, and with David Chandler, I worked on totally different statistical mechanical things. And it was fun. We worked on the way water, plays a role in driving protein folding, some of the process of that. I worked on ways in which electronic transitions with relevance for solar energy could be better described using models for chemical dynamics. So there were very fun problems I got to grapple with, but I didn't quite bring the two into one grand problem together.
Tom, what would a grand problem in theoretical chemistry look like?
Oh, well, I would have settled for anything where we all just put our name in the paper, to be honestly. But we're just triangulating on whatever humble triangle I could come up with. They do point to them. I think non-adiabatic dynamics is one of the great ones. The electronic structures, treating strongly correlated electronic systems is a great challenge. Many people point to glass C dynamics, the way which very slowly evolving systems age as another grand challenge. Yeah, those are fine challenges, and my work has touched on some of those a little bit. But I've always been more excited about methods that enable, I think that I was always more driven by the can you actually make a better prediction? Can you actually make a better algorithm that'll execute on on real chemical problems? that was a big draw for me, as opposed to the most deep, the most thought-provoking, the most intractable problem. I liked finding problems that I think I could solve and developing methods that I think I could bring to bear on them, and going after those.
And this atmosphere, this was a fundamental science kind of world you were in. There was not, you
Oh
were not
yeah, oh
thinking
yeah.
about translation, applications, things like that.
Oh, absolutely, absolutely. And when I act like I'm such a practical guy, that's really on the spectrum
Right.
of impractical people. Like any casual observer would have seen deep fundamental science. But there's always resolution within resolution. Yeah.
To the extent that the Bay Area generally, Berkeley in particular, is always ahead of the curve in computation, was that relevant at all for your postdoc, would you say?
Yeah, they were. I wouldn't say it was really infused with .com culture or any of kind of that aspect of computation. The Bay Area is just, it's like Caltech. It's a storied university. Berkeley is. It's got a huge number of fantastic scientists, and it produces a huge number of fantastic scientists. And I was there basically for to take advantage of that environment.
What would you say your key contributions or findings were with both lines of research with each professor?
Yeah, I think that we, with David Chandler, I managed to take a method that had only been demonstrated in really simple systems, like very low dimensional systems, and I showed that you could take that idea, you could scale it up, you could implement it on a real protein folding like problem, in something that only had been applied in kind of 3 or 4 dimensions. I was able to apply in over 100,000 dimensions, and basically to a real at scale problem, and find some really cool results about the way water fluctuations can play a very active role in protein folding. You can basically have the protein will partially fold. It will induce a fluctuation in the water. That fluctuation will kind of create a cavity into which the protein falls. A very interesting aspect of the way water mediates the folding of the protein, as opposed to the protein driving its own folding. And teasing apart that story was something that I really developed new methodology to be able to do. So that was one fun story. And on the dynamic side, I worked extensively on taking methods that had been very effective for including quantum mechanical effects on one electronic surface. So if you basically aren't absorbing light and going to a different electronic surface, but instead you're rolling along a single chemical landscape. And I extended that. I worked to extend that to descriptions that would allow multiple electronic states, so that if there was an electron transfer, or there was an absorption of light, there are huge areas of chemical phenomena that were not captured by that original theory, and I worked on ways to extend that to wider swaths of chemistry.
Tom, your work on protein folding, did that get you thinking at all about human health?
In a sense, when you have to do a job application, you basically have to say, okay, here's what I've done. Now I need a really great way to kind of make that compelling. So when I was applying for faculty jobs, I was trying to take the tools that I had, developed, and say, okay, if this really works, what is something important that I could speak to? So it led me to, on the one hand, it led me to enzyme reactivity, which is something I worked on in my early stages at Caltech. As well as the way in which proteins not only fold, but ways in which they get across cell membranes, and they interact with channels that are dedicated to protein conduction. And so those are two areas that I was led to as a result of that postdoctoral work. Absolutely.
Now, in terms of your career path at this stage, were you completely on the academic track? Did you think
Yeah.
about industry at that point?
No, at that stage, I was completely on the, during my graduate years, I had the grand exploration of other jobs. But then for the postdoc, it was like, if I want to get a faculty job, I got to, there's no two ways about it. You got to focus. So I was very single-minded on that. I actually applied for jobs after just 1 year at Berkeley. The Caltech job came up, and there hadn't been a position in Caltech in theoretical chemistry for like 40 years. So I applied for that. And I was lucky to get it. And I then deferred for a second year, basically, to spend that second year at Berkeley instead of coming immediately.
Do you know what the backstory is? A 40-year drought in theoretical chemistry in Caltech?
Oh, it wasn't a drought. It's just they had a really strong group of theoretical chemists that they kind of hired at the start of their career, and they all just never
Oh, I
emptied the
see.
slot.
I see. I thought they didn't have one. Okay, that makes
Yeah,
much more
I
sense.
think Bill Goddard was my the next most junior colleague. So so they had a very strong commitment to theoretical chemistry, but they just hadn't had there'd been very little turnover.
In what ways did Caltech theoretical chemistry loom in your education up to that point? Were you aware of what was happening at Caltech? Was it a center of excellence? Were you following the work of some of your senior to-be colleagues?
Oh, absolutely. I mean, Caltech was one of the small number of schools I'd applied to for graduate school. So I had come as a prospective graduate student, in I guess 2000, and had a chance to, interview with all these professors, and then I'd gone off to, to the UK, and then I'd gone and done my master's, and I decided to go to Berkeley for my postdoc, and so I had awareness of them from that initial visit, but of course, everything I'd been working on for like 5 years up to the end of my postdoc was Feynman path integrals. That's all Caltech. The non-adiabatic transitions, the transitions between electronic states I was referring to. One of the canonical examples of that is electron transfer. There's only one name in electron transfer, Marcus. So really, chemical dynamics, Aaron Cooperman played a huge role in that, dynamics of water and in complex systems. Bill Goddard played a huge role in that. So yeah, I really knew these people and I knew their work and had a huge amount of admiration for them.
I've often heard it said that at Caltech for junior faculty, in order to succeed because it's such a small place, you have to be able to work by yourself. There aren't necessarily numerous people that are working in the similar field as you. So for theoretical chemistry, did you find that to be the case? How highly specialized were you at that point, would you say?
Yeah, that's interesting. I was definitely more focused at that point. You do have to kind of focus and make your own mark and don't collaborate a ton. And I never collaborated with any of my colleagues during my assistant professor years. That's right. It does remind me of a really funny story about, a story I find very funny with when I was a postdoc and I was considering taking the Caltech job. I talked to another kind of luminary in the field, Michael Klein, about my concern of going to Caltech because, I was scared I was going to overlap with Bill Goddard, right? Because the fact that, I worked on some aspects of dynamics and some aspects of simulation, and I was worried it was just going to be kind of too close to Bill Goddard. And his edge is like, Bill Goddard works on everything. You can't not overlap with Bill Goddard. Don't worry about that.
That's great.
So that really relaxed me. So you just got to make your own mark, and it turns out to be fine.
Tom, a cultural question. Did you get the sense that Caltech, hired you on the basis we're going to give you the support you need in order for you to succeed? In other words, are you on a path where tenure is the goal for everybody involved?
Oh yeah, that's undoubtedly, and that almost ratcheted up the pressure of it. They wanted you to succeed.
Yeah.
They give you they gave you a nurturing environment. They give you collegiality. They give you ample resources. They give you great students, and you got to execute on a successful research program and make a difference scientifically. But you can't. And not everybody has the same experience, obviously, but in my experience, they give you the football and you got to run with it, and you can't blame anybody else if that didn't. And in a funny sort of way, that increased the pressure. It's like, because it wasn't just me. It's like they so clearly wanted you to succeed as well that they were, kind of rooting for you, and you didn't want to let down the side either, in terms of that success. So it was really what you'd hope for, I think, in that situation.
So in theoretical chemistry generally, and for what you were interested in at that point, what are the startup costs? What are the resources that you need to get going as a junior faculty member?
Yeah, it's basically just people in a computer. So
so you're cheap. You're cheaper than microscopes and all of that stuff.
There's no lab renovations. We're not totally cheap because of the fact that computers are expensive and people are always expensive, and we still have decent sized groups. So it was the startup I had then is of course small by today's standards. It was pretty big by those days standards. Maybe factor of two off what a normal experimental startup would be. Kind of that difference.
On both the hardware and the software side, what are the most important systems to have at that point?
Software is usually not an issue. The software tends to be cheap, or you write it yourself, or you can get it pretty easily. The hardware side, I mean, you just want a computer cluster, and that's something that kind of changes every several years based on what's available. With increasing cloud resources, or GPUs versus CPUs, or on-premises versus other models. The initial thing that we went with was I purchased a cluster that was housed on campus. And, I kind of went with that model for much of my time at Caltech. And then, additional centralized clusters came available and used a hybrid of those. Never did a lot of cloud computing. During my time at Caltech, interesting, at Entos, we do a ton of cloud computing, but it's just different days.
In terms of federal support, what are the key agencies for you?
Yeah, that was one of the things, I worked on very fundamental sides of making and breaking bonds and methods to do that. So you can really justify yourself in almost any funding agency. So I think my first grant, thanks to a kind introduction from Rudy Marcus, was the Office of Naval Research. So that was, I think, my first grant. But then, Department of Energy, NSF, Air Force, Army, eventually the NIH. But it was really kind of those kind of physical chemistry centric things of, energy science, armed services, Army, Navy, Air Force. Yeah.
Tom, in terms of building a niche for yourself on the faculty relative to what your more senior colleagues were working on, what did you decide to focus on at that point, circa 2008, 2009?
Yeah. It was less a concern about differentiating from my colleagues, I would say. I relied on computing much more explicitly than many of my colleagues.
Would you say that's a generational issue?
Yeah, in large part. Although Bill Goddard, of course, does everything. So he of course was also doing that. But definitely in terms of, in contrast to. But actually, I think it's also unfair to say a generational thing. I mean, Aaron Cooperman was undoubtedly a very senior colleague of mine, but he was extraordinarily profound in the way he used, computing and embraced computing in his own work. So I guess I do want to take that back. I don't want to say it's a generation thing. I think it was it was the reality that I wanted to position myself at the interface of dynamics and statistical mechanics. I wanted to not only describe how complex systems, large numbers of atoms behaved on average. I wanted to describe how they did it in time, right? Aaron Cooperman had done dynamics, but he'd done dynamics in the gas phase. Same for Vince McCoy. So very small numbers of atoms. Bill Goddard did, many different complex systems, but there was, opportunity to really bring together fundamental novel methods for describing dynamics and doing that in things that, were kind of a protein with solvent, an interface of a battery, an enzyme at its work, genuinely complex systems.
Students at Caltech, undergraduates at Caltech, was computer science already the dominant major, would you say, by the time you joined the faculty?
No, everybody was hand-wringing about bioengineering taking over the world when I joined. And then, so it was a wave before at CS.
So that's what most of the students were interested in at that point.
There was a sway towards a lot of interest in that, and it was pulling away chemistry majors and chemical engineering majors. And I see these things as kind of generational things.
When did that happen? When did the computer science dominance really start, would you say?
Yeah, that's a fair question. I don't know. It must have been in the mid-teens, I guess, if I had to guess. But, yeah.
In the way that Caltech prides itself also on, having very thin administrative walls, your expertise in computation, were there opportunities to collaborate beyond CCE on campus?
Yeah, absolutely. Absolutely. I think I guess my first Okay, so first of all, when I was an assistant professor, kind of as we touched on, I didn't do a lot of collaborating on campus, I would say. Now, when I did start to collaborate, it was with experimental chemists in the department, and then it was with chemical engineers, and then it was with, biochemists as well. So I began to collaborate on those different, kind of starting within CC and then building out. I think my first forays outside of CE were then into the machine learning realm, computational and mathematical sciences, working with people like Animan and Kumar on our machine learning projects as those were taking off. But I once I started collaborating post tenure a lot of that was within CCE, I would say.
What were the research questions that compelled you to collaborate within an experimental framework?
Oh, I just think it's, as a tool becomes useful, you want to demonstrate its utility in a predictive mode, right? It's one thing to say, I have a great method to, explain something that you've already observed. It's very fun to then say, well, I can actually take that and I can make a prediction, and then you should be able to, make that molecule or test that prediction and see whether or not it's true and have a much more direct prospective version of validating that methodology and driving science.
What's the value, as a two-way street in terms of, for you, from a computational, a theoretical perspective, seeing that validation experimentally, and what's the value for the experimentalists having you as a resource to work on these things computationally?
Yeah, I think it's a very it's a good way to frame it. I think that when a collaboration first starts, there is that sort of kind of contractual nature. Why does this make sense for me to do it, and why does it make sense for you to do it? And if we can both agree that that it makes sense, then we kind of do it, sort of thing. And many times it comes out that there's certain things that you can easily probe computationally that are hard to directly observe. So you can get a better understanding under the hood that you can't easily see in an experiment. And then, once you understand what's going on under the hood, that can maybe give guidance to what should be done next in an experimental pursuit. So that's often the times why an experimentalist would be interested in that. And why a computational person would be interested in that is because it's a great way to see your science translate to application, right? You can actually impact important problems because of the tools you've developed. As a collaboration matures, then you're kind of, jointly thinking about a problem from two different angles together, right? And you're suggesting experiments and they're suggesting computations, and, you're just working as a team towards something bigger. So I think that's, good collaborations might go from that kind of contractual sort of mode to a genuine, meeting of the minds or kind of working together towards a problem in partnership.
Tom, would an experimental chemist come to you as a matter of efficiency to see if something works computationally, and then using that as a basis for figuring out if it works, quote unquote, in the real world?
Oh, yeah, all the time. Yeah, so that's a very natural mode. And you can't accept all those collaborations. I mean, sometimes that makes sense to do, sometimes that doesn't make sense to do. You don't want to just run a service operation where, you just run calculations or do stuff because somebody asked you to do it. I think that you have to see whether or not, everyone's time is precious and limited. So you have to figure out whether or not that activity is going to be on pathway with the bigger scientific program or bigger scientific mission you're trying to achieve. And many times it is, but sometimes it isn't as well.
So what would be a good example that stands out in your memory of an experimentalist coming to you and saying, work this out computationally, and then let's see how well it works in the lab? What would be an example of something that was compelling to you to do that?
Yeah, well, one of my favorite versions of that was with my colleague Bill Clemens, where we had been trying to look at how proteins get into the cell membrane. Just understanding, protein comes out of the ribosome, it's docks at a receptor on the membrane, it threads out a protein that gets inserted in the membrane, it loops through. That is, what leads to a folded membrane protein. which is just fascinating and cool and has all sorts of fundamental questions connected to it. Why does it go this way? Why doesn't it go that way? What's the biophysics of all this? How can I change that? Does biology use those changes? Many different things like that, right? And Bill kind of said that, we were having a conversation and, I mean, he pointed out that, if you don't successfully thread in the right way, you're going to get degraded as a protein. And therefore, if you could predict the probability that something correctly gets threaded into the membrane, that should correlate with the observed experimental expression, the actual amount of protein that, a cell makes. So that is a pretty direct readout, right? If you can actually, high probability, low probability, more protein they see, less protein they see. And that led to, a very nice connection between the underlying modeling and a very important question about how to actively, introduce mutations that will drive higher levels of protein production, which is critical to a lot of membrane protein science. So that was a great example of that I really enjoyed, and we worked on that for a long time.
Tom, tell me about building up your research group, the kinds of graduate students and postdocs who were both attracted to what you were doing and who you wanted to see in your group, the kinds of life attributes, areas of expertise that were compelling to you.
Yeah, that's very good question. I found that Caltech is really replete with incredibly smart students. So I definitely was very spoiled and enabled by the tremendous quality of the students. That it basically means you can do more stuff because they can execute independently of you, and you can basically achieve more as a group, and you can do better in every single one of those directions because of their capabilities. The sort of people that I really found I quickly liked is, there's lots of people that are smart, but not everybody's resilient. Not everybody is optimistic in the face of, problems and adversities that inevitably come up, right? So those are the people that I really found myself recruiting. And once they're in the group, those are the ones I found myself really thriving because science it's just one thing going wrong after another.
Right.
And, right. And, and if you haven't learned to deal with that and grapple with that and struggle with that, then you have to go through that learning process. And people that are, predisposed to handling that well, tend to be very successful. And those are kind of people I like working with.
When it was time to come up for tenure, as you were taking stock of your own accomplishments at that point, what was the case you might have made just to yourself at that point?
Yeah. The thing at my colleagues at Caltech made it pretty clear that somehow in some nebulous way, you have to have taught the world something about chemistry or about science, right? There wasn't some amount of funding you had to get. There wasn't some number of papers or, where they got published that mattered.
It's discovery.
Yeah, you had to have a story where you could really say, people didn't understand this. And because of everything that I was doing, we taught them this. And it makes sense and it holds together and it is an advance in our understanding. And that is exciting. And I achieved that. And I'm associated with having achieved that. And that was great. I will say that my tenure talk was the one talk that weighed on my mind more than any talk, because it weighed on your mind for years, right? You knew you were going to give that talk the day you showed up on campus, right? And you knew it was about 4 or 5 years away, and that talk weighed in my mind a lot over those years, because that would be the point at which you have to make that case not only to yourself, but at least in the scientific story, make that case to the audience. And so that was.
That's such a key observation. That funding, all of the metrics. What you're saying is that's all window dressing for the discovery. It's the discovery that matters.
And it's a mark of Caltech's quality that they look at it that way. Right. Other schools, are much more focused on those numbers. And, I think it's really part of Caltech's strength as an institution that they do not, you don't even put your funding numbers in the package. They don't want to see it.
Yeah.
Right. They want to know whether or not you have taught the world, so you discovered something new.
So what was that story? What did you tell during your tenure talk?
Yeah, and that was the other thing. You've done a lot of papers by that point. You got to choose one to really go big on, right?
Is that the case?
So
Did you see it that way? That it wasn't a connection through all of the papers that you can tell one story? That's really the way to do it, to look at one paper and expand upon that
it's not so much as one. It has to be one project, I would
project.
say, or maybe usually you don't want to go there with just a grab bag of stories, right? Here's
Right.
3 minutes on this, here's 3 minutes on that. You don't want to do that. What the best case scenario is when you have one rich, interesting story that takes a great arc and lands at something that is both true and non-obvious and compelling and a culmination of all this effort. So that is the more ideal situation. So I didn't talk about multiple projects, even though I had multiple projects. I talked about one project. It could have been multiple papers in a series. And in a way it was. There was methodology papers, and then we applied those methodologies in one story. And it focused on understanding the way in which protein motions participate, or basically enzyme motions participate in an enzyme catalyzed reaction. Is there, are the ways the enzyme moves during the course of the reaction, are they somehow just random fluctuations that lead to a higher probability of reaching the reaction barrier and getting over? Or are they more directed motions where you have not just individual fluctuations, but you have some sort of collections of motions that will funnel you over that reaction barrier? That seems like a very odd question to arrive at, maybe in a vacuum, but there was really active literature on that, where lots of people were saying, one of these things happened. Lots of people were saying, no, these other things happen. And it was a great situation where if you had the right tool, you could actually cleanly say, well, here's a measure of statistical correlation. Here's a measure of dynamical correlation. Here is the enzyme reaction that we all agree on as being, where this should manifest. Let's look at these two correlation functions now that we have this tool that can actually access that. And let's see which of those two things you see. And we were able to show really compellingly that there's statistically very extended correlations throughout the enzyme that explained all the experimental observables. But the dynamic correlations that many people had been invoking were just utterly absent. If you go 1 or 2 angstroms away, they were gone. There was no, dynamical correlation effect. So, that paper, was a very substantial, nail in the coffin of that idea that was the way in which enzymes were working.
And to clarify, this is a theoretical discovery that's borne out experimentally.
Yeah, that's exactly right. It was a great example of one of those things where it's hard to have the experiment to directly observe, these two different things. They're two different mechanisms, and you want to be able to explain all of the data, but the experimental data was making it difficult to resolve between those two underlying mechanisms. So additional theoretical analysis was had the opportunity to perform that resolution.
Tom, in the narrative so far, it's all fundamental science. You're on an academic track. So wherever you place the deepest seed in the origin story of Entos AI, would you say it's pre or post tenure?
Post tenure, absolutely post tenure. Yeah.
So even the experimental work that gave you that validation that this stuff actually is working in the real world, that didn't put you on that track, even conceptually.
No, a lot of people are like, well, why don't, maybe you should open. Have you ever thought about having a lab? Have you ever thought about, doing this, doing experiments yourself? And no, that didn't appeal to me. Because one of the things I liked about being a theorist is I could work on many different problems. And as soon as you get a lab that's dedicated to one thing, it's like, it's really hard to kind of
locked
repurpose
in.
that. Yeah, I kind of locked in. So no, that never appealed to me. I would say the deepest seed for where Entos came from. There's one conversation that I've been collaborating with Fred Manby for a long time. We had been collaborating on very fundamental science things about ways to describe. I think I mentioned in the origin of the word entos and these embedding methods, and the and he was visiting Caltech on sabbatical. He spent a year on sabbatical, right? And we were, walking around and going on one of our walks and talking about what we should, the methods we had and what they're going to be good for and how we could, what methods should we develop for what important problem. And we were outside Millikan, just in that little courtyard there by the chemistry admin building, and we hit upon this idea that if we were, there were kind of the canonical things you worked on as a theoretical chemist, right? There are you want better accuracy. You really want to say, how can I put more physics in there in order to get better accuracy? And what we realized is that if we kind of had put that amount of effort and that amount of creativity that we were towards the problems that sort of the field were most naturally posing, if we pointed that towards what we thought was the most practical outcome, right? If we didn't prioritize it in terms of what the field saw as the most important challenge, but instead we said, what if we took all of these, this creativity and all of this understanding and all this, effort, and we pointed it at what would be most practically important for industrial scientists, for example, as opposed to, answering the question of the day academically, would we be doing the same problems? Would we be choosing the same problems? And we concluded, no, we would not be doing the same problems. We should use all that creativity and all that insight, but we should be going after basically more mass market questions that will touch on more people and have more of a translational opportunity. And that was a very important conversation that kind of, you're post-tenure, you're liberated to go after the questions that you care about. You're not handed the questions by the field as much anymore. And I thought it was a chance to go after a question that had the possibility of having more real world impact. And I think that was really the first version of that. We both really embraced that notion and began developing methods and then software and then everything else after that kind of followed that line of reasoning.
Tom, the timing of this conversation and the way you responded to it, do you see the fact that it's post-tenure as happenstance, or did tenure give you a certain intellectual freedom to pursue things that you might feel otherwise too constrained to do?
Oh, it absolutely wouldn't have happened pre-tenure. Pre-tenure, you're laser focused on a 5-year timeline. You're like, I don't want to think about anything that, I'm going to get tenure. I'm going to answer a well-defined set of questions, and I'm going to make sure that I execute on that. Post-tenure, you're suddenly like, wow, I'm going to live 40 more years. What am I going to do? It's time to reevaluate your research program. So that I think was part of that, breathing space. You have the security of the job. You don't have to worry about that. You don't have the timeline hanging over your head. And you have the chance to say, okay, now, with this different set of constraints than I've been making decisions on before, with this different set of assumptions and constraints, would I answer the questions the same way? And the answer was no. You answer the questions differently because your situation is different. And I think that was why it happened right on the heels of tenure.
Now, initially, did you think that this was something that you could pursue within the framework of a Caltech career?
Yes, and I did. All the way from 2007 to 2020 and then 22. Absolutely. It was basically a decision that. Sorry, I think I said 2013. Tenure was at 2013, but right. All the way between 2013 all the way to 2020. It was just a very abstract idea about the logic for problem selection that manifest in lots of new projects. I started more battery projects. I started more of these, biology projects with membrane protein expression. I started many more collaborations at that point, trying to figure out where the tools could be useful and where they were useful. It wasn't clear, just because you want to do something that's more relevant, you don't know there's many ways to be relevant. And, it took a while to figure out exactly how I could sink my teeth into that aspiration.
from the earlier questions where you said you were laser focused, right? The discovery never ends. What were some of the key connecting points from the pre-tenure focus to the things you started to look at after tenure as you were coming up with this business idea?
Yeah, I think that the you know, the the very kind of tenure pre-tenure arc is here's an important problem for which there is no method to solve that. I will invent that method. I will apply that method to solve this problem and demonstrate that and teach the world something new because that was an important problem to solve, right? Kind of do that. I think that that continued to be the natural way in which I framed questions ever after, even after tenure. I mean, all of my research programs still kind of had that shape to them. But I think I allowed myself to do that in a way that I would be collaborating more. I allowed myself to do that in a way where on the spectrum between is this the most creative method ever versus an application of that method, I would allow that to, I would allow it to draw that balance a little bit more on the practical side of actually addressing a real world problem. So in the way it kind of played out, it was just a shift in the balance of the factors of designing a project from the way I did it before to the way I did it afterwards.
From batteries to biology, did you find yourself talking with a wider range of scholars at Caltech?
Oh yeah. That really was. I think in a very, I definitely took advantage and benefited from Caltech pre-tenure, but one way in which I didn't, take full advantage is through collaborating with my colleagues. And it was a wonderful process to work with so many of them in different ways during that post-tenure period. Absolutely.
So from 2013 to 2020, when did it start to dawn on you that maybe you would have a full-time life beyond Caltech?
Oh, that didn't dawn on me till after 2020 and sabbatical. I went on sabbatical with the assumption I'd be returning to Caltech.
Oh, interesting.
This was something that was, evolving within me that you can kind of look back and maybe see the seeds of it. But no, I didn't leave on sabbatical with the expectation that I'm making a leap into an entrepreneurial career. I was like, well, I need this is something I'm really excited. I think I did have a hunger to somehow create a business or somehow create a company using the tools. But I saw that as an expression that the tools matter, right? It's one thing to worry about whether or not, and you try not to worry about it unduly, but whether or not the work gets recognized, the way the paper gets cited, whether or not you're publishing enough. What metrics should I be optimizing for in my science, right? Do I want to do the most students? Do I want to do the most projects? Do I want to write the most papers? Do I want the most citations? Get the most awards? And one very simple answer to the question of relevance is, can I solve a problem that translates into something that can stand on its own 2 feet, right? And if you have a solution to a problem that could be the kernel of a company, that's a version of success of a translational idea, and I think that drew me in, and I know that I did during that time increasingly want to have one of the ideas that I worked on in the lab make that leap to a startup.
Tom, how did your evolving interests change the research group, the graduate students that came in that are on a 4 or 5 year timeline? While you're rapidly changing, they come in at a time when, you're doing things earlier in your career that they might be connected to. How do you manage that?
Yeah, I think, well, I mean, the most important thing is you try to do a good job for your students. And, none of this happens on a dime, right? It's a graduate student will work on, in sequence, over a course of 5 years, they'll work on kind of maybe 3 or 2 lengthy projects. Might divide that into different papers, but really you kind of do 2 different project areas. And I think that the actual content of my research program um, didn't change beyond recognition. The same sort of students were coming, the same sort of students, the students that were coming, indeed could work on similar sorts of projects, but there were just more collaborations and more, ways in which those methods that were developed could be applied at the end of the day.
So when you went on sabbatical and this revelation came to you, what was it?
Um, I think that, well, I think the basic idea is that when we went on sabbatical, you got an idea, you have a code, you like the code, you think it works, somebody's going to be willing to license, that's great. And you're like, cool, right? It's getting out in the world, and I'm proud that it's getting out in the world, that's great. But then sometime during that first year, you're like, I think it's as good as anything else out there.
Uh-huh.
And I think that actually works, right? And the fact that it actually works, um, it's really exciting. And you recognize that its probability of working at the end of the day is directly tethered to whether or not you're going to throw your weight behind it. And I think that basically.
And what works, Tom? Is it an idea? Is it an experiment? What's that match that was lit at that point?
Yeah, the basic idea that machine learning in the way that we were doing it and computation in the way we were doing it was providing guidance on the design of molecules in a way that was better than other people could do. That was what we convinced ourselves. And the implication of that is that there's two things you can do with that. You can either try to bundle that up as a software package and try to convince everyone that if they bought your software, they would have that benefit of better design of the molecules. Or you could say, well, if it actually works, let's just make better molecules. Let's just do it ourselves and, take that in-house and enjoy that differentiation and use it to arrive at better molecules faster. And it was that latter strategy that, in a commercial sense has much higher value, of course, and in a process of doing it sense is much more fun. Instead of just running around trying to convince people that this is so great and they should buy it, you can actually just use it and execute with it and actually make better molecules. And then those molecules can stand on their own 2 feet. And then it's like making the prediction. You don't have to explain what's going on under the hood. They can see it at the end of the day. And if they like it, you've won. So I think, what happened during that sabbatical period was that, we had the opportunity to do something that we thought could be successful. It would be, it would emerge from the science that we had been so excited to pursue and so proud of, and could actually make a difference on problems that mattered in the world. And and all of that hinges on whether or not you're really going to commit to it yourself, right? If you just hand that to somebody else and say, hope it works, that's a lower chance of it actually happening than if you say, well, I'm going to do this and I'm going to try to bring people around me to come and to help me make it work. And that the latter approach is what we do.
I imagine that's a much stronger case to a potential venture capitalist that they see how much you believe in it. You're throwing your whole career behind it.
And every recruit. So when you do a startup, you're recruiting lots of people, and you're recruiting people that could go to lots of other jobs, and senior people and junior people, and they can see that's a big difference. Yeah, they can see that. It's just a great example of how risky things fail, but you can actually control the odds substantially by some of the choices that you make, right? By committing and assuming more of that risk, you're making the outcome more likely of working out. So it's an interesting aspect of it.
Tom, so I understand the timing. When you come back from sabbatical, is the point between then and, from a few months ago, basically the lag time of winding down your group? Is that the objective at that point?
I never did come back from sabbatical. So my sabbatical extended from kind of April 2020 to April 2022. I initially went out for 9 months, then I bumped it out for a year and a half, and then I bumped it out for 2 years. But sometime in that second year, I communicated to the university that I wouldn't be returning to my full-time position, and they're very supportive. I think we talked about that, and so I never did come back.
Tom, last few questions just to wrap up this excellent series of discussions. Was it a light bulb moment when you said, I'm not coming back, or that was also sort of a process? Was there one thing that convinced you, given all of the risk, given all of the uncertainty? Was it a process, or was there one thing where you said, that's it, I'm doing this with, jumping in with both feet?
The funny thing about a sabbatical, maybe even a sabbatical in a pandemic, is you can allow yourself not to look at that reality. It's like Schrodinger and his cat, right?
Yeah.
You can put it in the box, you'll have to look at it, something's happening in there, and you can kind of say, well, I don't have to worry about that question for like 2 years, so I'm not going to worry about that. I'm just going to allow things to evolve, right? And then and by the time you are driven by the requirements of the tenure limits, and by just the requirements to answer that question for yourself, the reality has shifted to the point where I think I do want to do this. I think I am at that point. So I don't know the exact moment where I toggled from one status to the other, but I do know that when I did take stock of the situation and did have to reach that decision, it was no longer a close call. It was very clearly the right thing for me to do to pursue this, and I was very excited about that.
Between student internships and supporting junior scholars, how do you compare the pleasures of mentorship in business with professorship?
The shoe's on the other foot, I would say. As a professor, I was tenured, I was experienced, I'd seen students, and they, many, a first-year student will come in, and then you will teach them, and you will help them, and you will mentor them. And in a way, I was always in that, providing mentorship. You receive it from your senior colleagues, but, after 15 years, you're not, you're more or less take the training wheels off. When I went into a startup culture, I didn't know anything. I mean, I would learn so much month on month, in terms of how this all worked, what I should be worrying about, what it takes to build a company, what are all these jobs and what do they do, and how do they fit together. Just the sheer amount of mentorship and learning that I needed was a very different. Like I said, the shoe was just totally on the other foot in terms of who was learning. Even the people that I would hire and supposedly be, a mentor for, they had worked in the industry, so they were telling me how it worked. They were mentoring me. So I think it was a very, you try to be a supportive leader. You try to, be a good member of the team and a good leader of the company. But I definitely feel like I've been mentored more than I've mentored since actually entering the startup world.
Tom, what stays closest to you on a daily basis from all of your years in fundamental science? Either the theory, modes of collaboration. What's the greatest influence to you on a day-to-day basis?
I think there's two things. I think there is an underlying faith in the fact that things might seem very complicated, but you can figure them out. Nothing is too hard to understand or to figure out. And that gives you a lot of confidence into kind of going into new fields. Sure, you won't know anything when you first get there, but, building on the base of what you've done in academics and at Caltech, I always have a certain level of confidence that, once I read the books or once I talk to the right people or once I dig into it, I will be able to understand it. And that is, it's kind of a life preserver that you can rely on that as you go into areas that are new and scary. I think the other thing is that, Caltech imbues you with the idea that you should go after what you think are the big problems. You should go after what you see as the ambitious challenges. And as you do that, you should do that with an integrity and a rigor that is rooted in good science. And I think those are things that I do carry every single day, and I do utilize in the decisions and in the way about which we pursue the objectives in the company.
Tom, in the way that you articulated that initial idea or realization that you came upon something where you realized you and your colleagues could do this better than what was out there, generally relative to competition. When, if not now, what's your timeline on the market coming to that realization itself?
Well,
Or are you already there?
Well, yeah, no, I think that's right. I mean, I think in some sense, getting that next round of funding relied on at least some people thinking you might be right in that, right? And then, building a company around that involves convincing a bunch of people that decide to take that job and to do it with you that you might be right in that. And then executing on that and taking, getting lead compounds that are exciting, is further proof to even more people that, hey, maybe that really does work. So I think that you're casting a wider and wider net of the people that you might convince of that idea.
Tom, one last question to tie together past, present, and future. In the way that you had that dichotomy of tenure, where this was not something that you could have thought about pre-tenure, is there some threshold you're looking out X number of years to the future where you say once you cross that Rubicon, you will open yourself up to new ideas that, might not be available or even feasible to you now?
That's a great question. One thing that I've become much more comfortable with the idea that I don't really know what I'm going to be doing in a couple of years than I ever was before. I mean, that's like, that's the worst possible notion of a pre-tenure professor, right? It's like the last thing you want to embrace as an idea. So I think that, this is something that I feel very fortunate to be doing. It's something that I want to make successful and that I want to continue doing for a long time. But unlike an academic career where you are, have control over very long timelines, you don't have that here. And by making this switch once, I have confidence that if circumstances require, I'll be able to make a similar transition in the future. That's a very new mode of operation for me in my career, but it's one that I'm much more comfortable with, and it keeps you kind of feeling young.
Tom, I want to thank you so much for these conversations. There's a lot of pride at Caltech for what you're doing right now, and good luck.
Thank you so much, David. Thank you for your thoughts.